I'm going to go over a practice quiz related to Chapter 6. In this problem, a student puts a book on the seat of the car and is driving at a given speed around a curve. We are given the coefficient of static friction, and then we're going to be asked a few questions. First thing, is the book accelerating during this time? Now it says constant speed. However, the book is not going in a straight path. The book is changing direction. Which means that the book is changing velocity. So yes, it is accelerating. Alright, draw a free body diagram for the book as she drives around the curve with an appropriate coordinate system. Alright, so we're going to do a rear view of the book. From the rear, well, you wouldn't be able to see it because it's in a car, but imagining that we can see it, our X-ray vision. And then if we think about this book going away from us and making a left-hand turn, if it's making a left-hand turn, that means this is the positive R direction. There has to be some force in this direction. There always has to be a force inward, in towards the center of a circle if an object is going in a circular path. This book it's not sliding, so there is a static friction force. Another clue that there's a static friction force is that right there, of course. And now we are, and then we have a Y direction. And we're asked to find the size of the static friction force. So we can sum the forces in the R direction. So that's equal to MAC. So Fs equals the mass of the book. The mass of the book is 13.5 newtons divided by 9.8 meters per second squared. Okay, that's the mass. And then A sub C, we know, is equal to V squared over R. So 12 meters per second squared divided by 50 meters. We get an Fs of 3.97 newtons. Okay, and by the way, Fs max, if you should happen to calculate it, is 9.45 newtons. However, the maximum static friction value hasn't been reached. In other words, the car could go faster without the book slipping. That's what this means over here. So we're not worried about that. Okay, so sometimes you have information in a problem that you end up not using. If you were to find the maximum static friction, that would not be the answer to this question being asked in Part C. Alright, move on to the next one. The moon is a given distance away from the Earth, and it takes around 27.3 days for the moon to make one revolution around. So based on that, can we find the acceleration? Well, as we saw on the last slide, A sub C is equal to V squared over R. Now, V is equal to really it's the speed, so we'll say that's the speed. I know we use V for velocity a lot, but we can say V is velocity, and V without the arrow over it, that's the magnitude, that's the scalar form, that's the speed. Alright, so that's equal to distance over time, which is equal to 2 pi r over that time for one revolution. So that's 2 pi times 238,000 miles, 1,609 meters per mile, and then that's happening in 27.3 days, 24 hours per day, and 3,600 seconds per hour. And so we get a V of 1,020 meters per second. And you might want to break this down into parts, calculate the distance, and calculate the time separately in your calculator. You can certainly do it all at once. You just need to make sure you use parentheses correctly. The parentheses that I've shown here would not be the quickest way to do the parentheses in your calculator. What you really need parentheses around would be this to here in your calculator to make sure that calculates correctly. So then A sub C is equal to 1020 meters per second squared. And if you did calculate that radius separately, then you wouldn't have to repeat this. Oops. Sorry about that. And so, there we go. And so we get an A sub C value of 0.00272. Units are meters per second squared. Alright. Draw a free body diagram for the moon. Alright, so the moon is out here, and maybe the Earth is down here, and so the force of gravity, so the moon could be traveling around in a circle like this, and so there's a force of gravity, and so that would be the R direction. Okay, so there's not just one correct way to draw this, there are several. And now we're supposed to use Newton's second law to determine the force of gravity. Alright, well, the second law, F equals ma, Fg equals the mass of the moon, 7.35 times 10 to the 22nd kilograms, times our acceleration from above. And this comes out to 1.98 times 10 to the 20th newtons. That's a rather large force, which makes sense, because to get the moon to keep changing direction, it requires a large force. Alright, now we can calculate the same thing. Okay. So in D, we're calculating the same thing we did in C, we're just calculating it a different way. So force of gravity equals G m1 m2 over r squared, and so that's equal to 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared. And then we put in the mass of the Earth, times the mass of the moon, and then we divide by this distance. We have to square it. I know it says radius, or it says r here, but it's not really a radius, or it's not, I should say, it's not the radius of the Earth or the radius of the moon, but it's the radius of the circular path that the moon makes around the Earth. And so that's why we use the distance between the Earth and moon. When we calculate this out, it comes out to 2.00 times 10 to the 20th newtons. Very nearly the same answer we got before. Alright, if you have any questions, feel free to follow up with me.